All right, Calculus, welcome to your notes video for Thursday, October 14th, 2021. I am not with you as I am quarantined pre the surgery tomorrow. We, folks, have a great lineup here of videos and sponsors ready for you. So first off, take a look. Crystal Light Pure Energy making its 2021 debut as a sponsor. Noon Energy, Cliff Bar, Peppermint Bark, seasonal flavors now available. Mr. Apple not say no to these as a Christmas gift. Hint, hint, wink, wink, or we're going to let you fall down. And Laura Bar, all right. Cherry Pie, just 3 original ingredients. And in-house, we have a studio audience today, folks. So let's take a look at our in-studio class right there. Now, these folks, you know, you always get the best at in here at Yak Math Videos. These folks have promised to quiet down. I'm looking, though, at Marie there, the Aristocat, and the Minion. You got to watch out for them. But, folks, we have an in-class in-studio classroom are ready to learn. All right, they are here with you, many teaching assistants. My favorite being the Minion. All right, so folks, you have this in your possession. This is just a notes template, and I think you should write on a separate sheet of paper the notes that we're going to have here. This is section 2.5, and section 2.5 we will accomplish in one day. Here, it's all about continuity, and we talks about continuity. A function is continuous if I can make the graph of said function without picking up my pencil. Think about your standard parabola. All right, you just make the U or the igloo without picking up my pencil. Think about a straight line. Think about the absolute value functions that we made in college algebra. If I have to pick up my pencil for any reason, or if I can't, if I have to start my graph at a certain place and I can't go anywhere to the left or to the right, then we have a discontinuity. F of x is not continuous in some region, some area. All right, so what I've done is I've written these notes right here. So let's talk about the section 2.5 examples. The first two said, determine if f of x is continuous. If not, state the location and type of all discontinuities. All right, so number one, there is the function, and what have I done there? I have simply, well, what I should have done. All right, remember, you can't divide by 0. So you're thinking, what could make this function discontinuous? And dividing by 0, a big no-no. So what I did is I factored both the top and the bottom. The top and the bottom both factor. Here's how the top factors. Here's how the bottom factors. And that's really important because I want you to name the discontinuities. X plus 1 over x plus 1, that cancels. That is a removable discontinuity. We kind of showed on Desmos how that would happen. It would show it, but when you got close to -1, it would say undefined. All right, so we got a removable discontinuity right there. Okay, again, you can cross those off. You set it equal to 0. We would have called that a hole in college algebra. We're going to call that a removable discontinuity. We covered it up. We removed it. Set x plus 3 equal to 0. That did not get removed. So -3/4 is a vertical asymptote. So if I have a removable discontinuity, if I have a vertical asymptote, f of x is not continuous. F of x is not continuous. And I have these 2 points that interrupt my graph. All right? That is the name of the game. So again, pause this whenever you need to. Make sure you have those good notes down. This is great prep for that second quiz of the chapter. And ultimately your exam. All right, here's number 2. F of x is equal to x squared minus 16 over x squared minus x minus 20. Factor the top and the bottom. Notice that the x plus 4s would cancel. That means x equals -4 is a removable discontinuity because the x plus 4s canceled. They got covered up. A hole gets covered up. I removed it. And so, hence, it's a removable discontinuity. Set x minus 5 equal to 0. and you get x equals 5 is a vertical asymptote. Thus, f of x is not continuous. All right, all right. Let's keep going here on number 3. F of x. This is a piecewise function here. And what are we doing on 3? Let's take a look on 3. Determine if f of x is continuous. If not, state, what does it say, location? What type of discontinuity do you have? Okay, so first off, from the left side of 2, x is approaching 2. It's getting as close as possible. You know, what we would have done in... This one looks a little bit different because you have when x is actually 2. So on this one, we're just going to plug 2 in for x. I know it can't be 2. We would use an open circle there. Plug 2 in for x right there. Get the square root of 4, which is 2. Now when x is actually allowed to be 2, plug 2 in for x. What do you get? Oh, you get 2 as well. So it's definitely continuous at that part. And lastly, plug 2 in for x from the right side there. Plug 2 in for x right there. And look at that. You get 2 again. Left side, right side, and when x is actually 2, it is also 2. Thus, f of x is totally continuous. All right? Now, let's look at number 4. Now, let's say you'd have gotten like, you know, because that's technically an open circle. That's technically an open circle. Right, actually, let's skip that. So that's a very, I'm going to cancel that thought there. That's a very interesting, unique one. Let's go to number 4 here and see how it's different. Okay, so x is allowed to be 0 here. So what did we do in college algebra when we graphed these piecewise functions? X is less than or equal to 0, so we would have said 0. We would have said -1. We don't really care about the left side of this. We're not actually graphing it. We care about these transition points of 0 and 2. So when x is 0, y is 1. And that's first equation. Remember, we labeled these in college algebra. We labeled them 1, 2, and 3. All right, the second one, I'm going to plug a 0 in for x. We didn't even think when we graphed this, we didn't even think about what we're going to plug in for x. We always used the lower bound and the upper bound. All right, if you hear any rumblings, that's our other teaching assistant, Yogi. He's a little more vocal. Yogi, can you say hi? Say hi, big guy. You can hide underneath. Okay, underneath the table is where we're gonna go until the mailman comes. Then you'll hear him. All right, so I'm gonna plug 0 in for x and 2 in for x. And when x is 0, y is 2. So what's gonna happen? It's gonna jump. There's going to be a closed circle at 0, 1. There's going to be an open circle at 0, 2. So it is going to jump from 0, 1 to 0, 2. I don't get the same y value twice. It is not continuous. All right. Now, there could be just one jump discontinuity, or there could be 2. And how do we figure out if there's 2? Well, we plug 2 in for x right there. Again, there would be an open circle at 2, 0. And there's a closed circle at 2, 0. So notice I get 2, 0 twice. So it's actually continuous when x is 2. I have a closed circle, and over a closed circle goes an open circle. Well, it still stays closed there. All right, so f of x is actually continuous at x equals 2. I get the same y value twice. But there's a discontinuity at x equals 0. And what happens again, if we look at this graph, it would jump from 0, 1 to 0, 2. All right, there'd be a closed circle here, open circle here, but I still jump. That is a jump discontinuity at x equals 0. And in college algebra, I told you that sort of analysis was going to come in calculus, and here it is. All right, 5 and 6 ask us, where is f of x continuous? Where is f of x continuous? It's essentially asking for the domain. All right, so where is f of x continuous? Let's zoom in here. So this is a square root function. I'm allowed to take the square root of 0. And so I set what's inside the square root equal to 0. I get x is 3. Now be careful here. If I plug 4 in for x, I get the square root of -1, which is a no-no. So the largest value of x is 3. So I could say x is anything 3 or less than or equal to 3. Well, I would write the domain like that. Domain is negative infinity, not including negative infinity, 2, 3, inclusion there. So f of x is continuous on that interval. F of x is continuous on that interval. All right. And 6, we are not allowed to divide by 0. So I set the denominator equal to 0. X cannot be 2. So the domain is negative infinity to 2, union 2 to infinity, not including 2. So f of x is continuous on, we are going to use intervals for continuity. To describe where f of x is continuous, we're going to use intervals and not set notation. All right, so 7 is an interesting one. We've done this one before, right? We've done this one before. Find the value of c so that f of x is continuous on negative infinity to infinity or its entire domain. So I need, just like we saw in, what was that? So that would have been number 3, right? We kept getting the same y value, or in the last one when x is 2, we got the same y value twice. If f of x is going to be continuous, that means this open circle at 2 comma whatever has to be the same y value as this closed circle, 2 comma. I'm going to get the same y value. All right, so I need the same y value when x is 2. There's going to be an open circle here, which is covered up by the closed circle. Thus, my parabola and my cubic function, however that would go, I can make it without, I can make the graph without picking up my pencil. So I need the same y value. So what I'm going to do is I'm going to plug 2 in for x, there and there. I'm going to plug 2 in for x, there and there. And I'm going to see what happens. Plug 2 in for x and then solve for c. And I did not continue with this. So you're going to get 6c is equal to 4. C is equal to 2/3. There you go. That is the value c. So that's f of x is continuous. All right, lastly, we have the intermediate value theorem. Okay, the intermediate value theorem. Use the intermediate value theorem to show that there is a root of the given equation in the specified interval. All right, so let's say I had this, because I would introduce this question via a little graph. All right, so you got x, you got y. Let's say this is 1. Let's say that is 2. And what sort of function? I have some sort of cubic function that's going to go like that. Okay? So clearly, I can tell this is an odd function because it definitely does not. This looks like a straight line. So anyway, clearly I can tell there's my root. There is my root. Is it 1.5? Is it 1.6? Is it irrational? But what I know is that f of 1, so if I didn't even graph this, and I had some interval, and I wanted you to check on the specified interval, 1 and 2, f of 1 is clearly a negative number, right? And f of 2 is clearly a positive number. Well, if my y value goes from negative to positive, or positive to negative, I had to cross what? I had to cross y equals 0, which is the x-axis. If I cross the x-axis, folks, that is a root. That's a solution. So I can see graphically that, yeah, I've got a solution there, 1.6 or something. All right, but I don't need to graph these. I can just say, hey, if f equals 1 is a negative number and if f of 1 is a negative number and f of 2 is a positive number, then it had to go from a negative y to a positive y, which means it had to cross y equals 0 somewhere between x is 1 and x is 2. So there has to be a solution to this equation between x is 1 and x is 2. That is what the intermediate value theorem is saying. So what you're going to, let's say I lost some notes. What you're going to do is, now you got to get this part right. Got to also make sure it's set equal to 0. Again, we want a y value of 0. All right. So plug 1 in for x. Show that work, you get a -1. So you're at the point 1, -1. Plug 2 in for x. And you're at the point 2, 12. You went from a negative y value to a positive y value. So here's how you're going to answer. You're going to say it crosses 0. So therefore, there's a solution. You're gonna show that you went from -1 to 12. Thus, it crosses 0. It crosses the x-axis between x equals 1 and x equals 2. That's all you got to show. All right, what's the exact solution? Who knows? Might be 1.6, just like before. We don't know, but we know there is a solution between 1 and 2. So we can kind of get closer, or we can use a computer to help us find that exactly. All right, so take a look at number 9, between also in the interval 1 and 2. So I'm going to plug 1 in for x. F of 1 equals, that's what you're going to do. You're going to say f of 1. You're going to say f of 2. Okay. F of 1 is another -1, and f of 2 is 15. It crosses 0. It crosses the x-axis. So there has to be a solution of x between 1 and 2. All right, let's take a look here. Now it has to be set equal to 0, so e of x equals 3 minus 2x is no bueno. I got to move the 3 and the 2x over. So this is f of 0. This is f of 1. Be careful, e to the 0 is 1. You have to get these y values correct. We'll be checking. So you're at -2. Then you have e to the first plus 2 minus 3 is e to the first minus 1. E to the first, Euler's constants, it should be celebrated. You can't celebrate in February because there's not 71 days, is 2.71-ish. Let's go to the official calculator here. Where's e? E to the first, 2.718. 2, and so actually it kind of rounds up to that. Anyway, that's bigger than 1. So from -2 to 1.72, it crosses 0. It crosses the x-axis. You just need to tell me that it crosses the x-axis, because I go from a negative y value to a positive y value. It doesn't always go from a negative to positive. I just keep giving you functions that are increasing on that interval. All right, sometimes you go from positive to negative. Folks, that is all your notes for continuity on Thursday. So get started on that homework set, the one that you can get started on, the one that I talked to you about. It's due date. Now I'm making this on Monday. So I've not told you to do the due date yet. I got an idea in my head, but I'm going to hold off on that. You know what the due date is. It is the following week. All right. Okay, that's your first video. This is Yak Math Videos signing out.